So we'll start by looking at the lowest energy possible, so rotational spectroscopy. And what we care about here from our rigid rotor model is what are the energies that our molecule can take. So the energies that we had depended on quantum number J, and we'll write everything in wave numbers. So this is the wave number version of the rotational constant times J plus 1. And this is, according to the rigid rotor, these are the energies that we have associated with this. And the other thing to remember is that there's this degeneracy of 2J plus 1 because we have 2J plus 1 m sub j quantum numbers, right? M sub j can go from negative j to positive j. And so rotational spectroscopy is very useful to understand structures of molecules because there is this relationship between the rotational constant and the structure, right? The rotational constant is directly related to the moment of inertia, and the moment of inertia depends on the shape of the molecule. So rotational spectroscopy is really useful that way. One particular application of rotational spectroscopy that I find super interesting is rotational spectroscopy is one of the main types of spectroscopy used to observe molecules in space. So it's a really key technique for astrochemistry. And I have several friends all across the country that use rotational spectroscopy to observe molecules of astrochemical interest, both using lab techniques and also using telescopes that can observe microwave radiation coming from space to observe transitions of molecules from space. Anyway, so this is our main model, and we can look at differences in energies, and we did something like this when we did the HCl lab. So we looked at the rotational and vibrations at the same time. So we'll get to that in this chapter. But one of our main assumptions here is that we assumed, to get these energy levels, we assumed that the bond length is fixed. And in an actual molecule, that's not true, right? A real molecule can move. The bond length can change, it can stretch and contract. Whether through vibrations, which we'll talk about in a little bit, or just from the molecule spinning around. And so as the molecule rotates faster, so as J increases and the angular momentum increases, I want you to take a second and think, would you expect the bond length to increase or on average or decrease on average? Okay, so hopefully you paused and thought about that for a minute. What happens is that as J increases, the bond length will slightly increase too. Because what's happening is we're going to talk about just diatomics to start with. As this molecule is spinning around, as it spins faster and faster, there's a force pushing these atoms apart from each other. And so the molecule stretches out a little bit as the molecule gets moving faster and faster. And so there should be a J-dependent term that we can add. So as J increases, we effectively will decrease the rotational constant. Right? The moment of inertia gets a little bit bigger because the atoms, or the nuclei in particular, are moving farther apart from each other. And so we do this, we add what's known as a centrifugal distortion constant. Centrifugal distortion being the name of this centrifugal force pushing the molecule apart. And so we do this by saying the rotational energy is equal to our rotational constant times J plus 1 minus a centrifugal distortion constant times, that depends on the square of this, J squared times J plus 1 squared. And this is a general way. We can continue to add further corrections as a series of polynomials. And rotational spectroscopists do this, and they go to very high orders. So we can say the rotational energy is J times J plus 1 minus D times J squared, J plus 1 squared. And then we can add extra terms like H, which depends on J cubed times J plus 1 cubed, and we can keep going with this. And spectroscopists do. We generate these very large tables of numbers describing these rotational transitions. So in general, what happens here is that if we drew out our energy levels, say this was J equals 0, j equals 1. This will apply more as you go further higher in j. Essentially, it brings it ever so slightly lower in energy when you apply centrifugal distortion. And so it matters more for things that are not rigid, right? The more rigid a molecule is, the less the bond lengths change as it rotates, the less this will matter. And it's going to matter for high values of J. The last thing I just want to mention, this video is getting a little bit long, but just to finish up with talking about rotational spectroscopy is when can we actually do it? So one of the requirements to observe a rotational spectrum is that the molecule must have a dipole moment. And the reason for that is basically the light is an electromagnetic wave, and it needs something to push against to cause the molecule to spin. So something like hydrogen or oxygen cannot be observed via rotational spectroscopy. But something like carbon monoxide or HCl, these do have rotational spectra that you can observe. The final thing is the selection rules, at least for a diatomic molecule, are that any transitions that occur have to have a change in J of plus or minus 1.